We haven't yet. Great. But we did hear about 3 other topics. So I'm going to start my talk just writing down 3 topics that I'm not going to talk about. Okay, so very unusual. What I'm not going to talk about is Flag cluster algebras in loop and tree amplitudes. So Flag cluster algebras in tree and loop amplitudes. And we've heard several talks. Mark, Qingling, Yorgos, Omer already talked about this. So we've been exploring, I'll just have a one-line summary of what we've been working on. In the papers, actually, one is with Andrzej. We've been exploring flag cluster algebras for both trees and loops, and we have interesting results that have been mentioned. Topic number 2 that I will not talk about is cluster algebras in cosmological correlators. And we've heard beautiful talks by Livia, who's here, and Tomek. I invite you to listen to the recordings if you were not here. And this also is, again, related to some work that I've been doing, and I will do my job and write the names of my collaborators momentarily. And the last topic that I will not talk about that we heard and that we're finishing a paper is Landau analysis for negative geometries. So on this topic, we've heard beautiful talk by Yara, and then on the negative geometries, and then we heard talks about Landau analysis from Matteo and Elia, who's in the audience. So these are kind of 3 topics that, so this is the paper to appear. This is also the paper that appeared 2 weeks ago, and this is 2 papers that appeared last year. And let me do my job before I start actually the talk and write the names of my collaborators on all these 3 topics. So this is our group in Brown. This is together with, Mark Spradlin. And most importantly, this is our postdoc, Shruti Paranjapi. Marcos Skovronik. And Hicheng Wang. I feel like now I've done my job. All these 3 people are going to be applying for jobs. Okay, Shruti, Marcos, and Hicheng. And the reason I just did my job is because I'm going to talk about 4th topic, which does not involve the group in Brown. So I feel guilty that I have to. I feel a little guilty here. So, okay, so the topic is Mellinology. Yeah. Yes, I'm here on 1, 2, 3. And who is this people? Sorry, I should have had the names written. Many of them are in the audience. Yes. How long I'm here? Did you say how long I'm here? Exactly. I'm leaving tomorrow morning, unfortunately. Yeah, but there's been, I urge you, if you were not here, watch these talks. Everything is recorded. It's been fantastic. But a lot of work. Again, 2 papers by these people have been mentioned. One actually is with Andrzej, who is here, who is no longer Brown. And then cosmological correlators, we had a paper with these guys. And this is the paper to appear that I feel guilty I haven't yet processed. It's been written by these guys, and we're working on making it publishable. So that's I did my job. Let me start actually with the talk. So Mellinology for energy correlators. Okay, so this topic we have not heard yet at this meeting. However, this might be what I'm mostly excited about. It's a huge subject, and this is the work in progress, which should appear soon with Kai Yan, who is a world leading expert on energy correlators, who is a professor in Shanghai Jiangtong, and Di Wu. And Di Wu is an undergraduate student in Zhejiang, undergraduate student of Ellis Yuan, Y from CHY. Okay, so why are we doing it? How did this project started? Well, this project started with Di Wu emailing me for last spring, asking for a summer project. He just, he might have emailed many of you. Normally I don't reply to these emails, but I checked Spires and he had a PRL paper with Ellis, so I said, why not? And he was an expert in Mellin, the paper concerned with Mellin space. And at the same time, I was in Santa Barbara at this great program, and I've been seeing that energy correlators are on the rise. I've been hearing the talks, and I talked to Kai, and actually Ian Moult, and they showed us some differential equations that they were finding for these energy correlators. I can refer you to Kai's talk in Stony Brook in 2024. There was a program, she wrote them, and I mean, she was showing these to us, and they smelled similar to the kind of differential equations that we've been seeing in n equals 4 Young-Mills integrals, and I will write them down. And, very nice, not much understanding. So then these two individuals came together, and we decided that maybe if we take these energy correlators and go to Mellin space, take the Mellin transform, maybe we could understand these differential equations that they were finding. So this is how this project arose. And it's based on, basically going to Mellin space is based on some paper we wrote in 2012, which I will mention momentarily, where we looked at Mellin representation for any dual conformal integrals. So now, let me write the plan of my talk. So number one, I'm going to do Mellinology. I call this Mellinology. It's a catchy name, I guess inspired by obvious person, Nima. So Mellinology for dual conformal integrals. And everything has been done in basically this would be a review for box, and I'm going to do box integral on the blackboard. In our paper, long time ago, 2012, with Miguel Paulus, who was a postdoc at Brown at the time. He's now a professor at École Normale in Paris, and Mark Spradlin. So I will start. So in this paper, we took at that time, long time ago, people were just discovering dual conformal symmetry, and people wrote a lot of interesting dual conformal invariant integrals, and we were like, why not go into Mellin space? So why did we do this? Well, at that time there was parallel progress by folks doing ADS-CFT and computing ADS-CFT correlators, and people were utilizing Mellin space. So we we were doing amplitudes. We took some integrals that were, popular in amplitudes community, such as integrals, some from Nima et al., and we went to Mellin space. Okay, and we worked out. If you open a paper, worked out a lot of examples such as box and hexagon. And interestingly, one thing that was striking, and this was relevant for today's talk is that we found interesting differential equations. So, for example, if you take a massive double box, just draw it, right? Something massive, then it's related by integral differential equation, something like this, to a hexagon, one loop hexagon integral in 6 dimensions. So there was some, at that time also people were exploring various different, so this is early days when our symbol paper was 2010, and it allowed a lot of computations to be done. So people were computing some of these hexagon integrals, and there were examples, and they were deriving some differential equations. But some of that were quite, I don't want to use obvious, but it's a nice way to see those equations. It was a nice way to see those equations by go to Mellin space. And so we were finding this on the nose. And, you know, I don't want to say our work was not, I mean, the culmination of this to me, just a second, came in 2024 in the paper by Anne Spearing, Wilhelm, and Qi Zhang, who computed all n planar n equals to 4 super Young-Mills amplitude, so all n, any number of legs, 2 loops, they have expressions, using these equations. So they took the integrals from NEMA, so the double box, double pentagon, and pentagon box, they really used this and wrote down, to me, this is like for me, for somebody who's been doing this for a while, this was really, really remarkable. Well, anyway, so this is why, to me, it was important to see these equations and why this was the motivation for going to Mellin space. Yes. Yes. This is elliptics and yeah. Yes. This is elliptical. Yeah, exactly. Perfect. So, very good. So, so this would be, so today I'm going to do, I need to watch the time. When did I start? 5 minutes. So I've been doing 10 minutes. Okay, very good. So I'm still describing the plan of my talk. So what I will do, so this is the title, the plan. So I'm going to do this for you on the board for the box. Most of you maybe know this by heart, so I apologize for boring you, but I will write a Mellin representation for a one-loop box, massive one-loop box. But you can keep in mind, everything I'm going to say here would be for simple example, then I have slides, and then we go and try to develop both sides of this correspondence that I will explain shortly. Okay, Mellinology, Mellin space for dual conformal array. Number 2 in the plan would be, I will show you, you haven't seen this. This could be a program, I think, by itself. So energy correlator integrals. So this is ordinary. You've seen this many times. Energy correlator integrals. Okay, I am going to write for you one integral. This is a subject which I think deserves a class by now. It's a huge subject, and the reference that I refer you everyone to is this review by 9119. It is review by Ian Moot and Washin Zhu. So it's 100 overview. Go there. Anything you need if you want to get up to date on this topic, please go there. It's amazing. So it's a huge subject, and this subject of energy correlators dates back to the 70s, and initially it was utilized to characterize asymptotic energy flux in QCD. It was revitalized by Hoffman and Maldacena about 10 years ago, who emphasized the importance of these observables in any quantum field theory. So for mathematicians in the audience, energy correlators are interesting observables, different from amplitudes that you've been hearing in this program, that are so these are some interesting observables in quantum field theory. And there has been a lot of progress computing these. I will have some of the credits on the slides. There's been a lot of progress computing them in perturbation theory, perturbatively, depending on number of insertions, number of loops, whatnot. There's a whole story and a whole lot of people working on that. But that's for theory. Now, there also, these observables can be measured in experiment. So to me, it's exciting because we just hired 2 high-energy experimentalists, and they care about these things. So it's kind of goes really the longest from real, somebody really works at the LHC to all the way to math folks. And a lot of activities. For example, I mentioned already Stony Brook conference. There is an Aspen this summer devoted to this topic, and there's a whole KATP program next January. So it's a really very healthy and exciting dialogue between the theory and experiment. Today, as I said, I will write for you one integral, the simplest integral that I will care in n equals 4 in a collinear limit. I will mention that. Okay, and then finally I will tell you the result. So what I will do, our result, which I will state actually right now, our result is that, I will state it so that you don't care. Our result will be that 3-point energy correlator on the left-hand side in n equals to 4. I'll draw it schematically and then I'll explain both sides. Could be written as some derivative of something like deformed box. So this is a schematic. I'm still trying to figure out how to present it better, but this is what I will explain. And I will do this for n equals to 3, and then n equals to 4. We have some preliminary discussion, and I will have slides. Okay, any questions? This is a good place to ask me a question. Thank you. Okay, perfect. Yeah. Okay. Touched by the care. Okay. Anything else? Any questions? Any other? Yes. Yes. We will talk about an QCD. Yes. This is a start. To me, this is a start. This is why I'm doing this Blackboard. Yeah. There is a story on both sides, and yes, to be seen. But I just want you to maybe appreciate. I think it's an important observation that I don't know, maybe some people agree. So connects one subject to energy correlator integrals that's completely studied differently from amplitudes to ordinary bulk. But it's not so simple because of this tilde and its deformed box, and I'll explain what it is. Oh yeah, Roro, yeah. Yes, the final answer on the left-hand side. I will have that answer. You know it actually very well. The final answer in terms of polylogs is related to the right-hand side. Yeah, exactly. And I don't. Again, I will have the answer on the slide. Yeah. They are infrared observers. Exactly. Yes, it is. Yes, perfect. Yes, exactly. Yes. Okay, so let me start with one. Okay, let me start. As promised, I'm going to start with one. So I try to write some basic formulas. So okay, so we're gonna go to Mellin space. We're gonna start with massive one-loop box integral. I apologize if many of you know this by heart. I will write it anyway. So 1, 2, 3, 4, 5, 6, 7, 8. We have x1, x2, x3, x4. And we're going to write an integral. d4x, x12, or x13 squared, x, so this should be familiar to everyone, x minus x1 squared, x minus x2 squared, x minus x3 squared, x minus x4 squared. Okay? Very good. Xij is xi minus xj. We start with the friend. So this integral was computed in when? When was this integral computed? First. Yes. 1993 by? Yes, thank you. Usykin and Davidichev. I look at you because I do it for you.
Yeah,
it's for you.
Look, show, but the massive.
Okay.
Is the massive.
Okay, yes, Usykin and Davidichev, and they write a formula, which, let me write it. Okay, 1 over lambda, this is from their formula, from their paper, 2 lead to rho u plus, I'm not going to write, everyone remembers this formula? What is lambda? Yes, of course. That for today, I'm doing one example on the board. One. Momentarily, I will show you all n gone in n dimensions due to work with Christian Vergu momentarily on slides. You have to wait. Okay, what is lambda? Yeah, what square? Yeah.
Square root.
See, I've been teaching undergraduates for 20 years. So, okay, I'm not going to write lambda. Rho. So this is the formula from the paper. Rho is okay. Okay, we have u's and v's. So everything could be at the end written in terms of u's and v's. U's are the cross ratio. I'm trying to figure out how much you want me to write and how much you remember. Could you speak up? Yeah. How much do you want me to? Yeah. So this is a function of u and v, which are their cross ratios. U is x12 squared, x34 squared, divided by x13 squared, x24 squared. And v is the same with some permutation. Yeah? I'm not going to talk about triangle. I'm going to talk about, yeah. So we all know and love this formula for many years. Now, yes, we will, yeah. We know and love. Okay, now let's write it in Mellin space. Do we know how to write this in Mellin space? Right? So this is a box. Let me call this box of u and v. Okay? Usykin and Davidichev function. How do we write this in Mellin space? This would be important because we will be comparing this. Box of u and v in Mellin space could be written as a twofold integral. I'm going to draw up all the factors. D delta u, d delta v, gamma squared, delta u, so gamma squared, delta v, times gamma of gamma squared 1 minus delta u minus delta v, u to the power minus delta u, v to the power minus delta v. Okay? So you can open our paper 2012. We do it for any dual conformal. We describe the process. In Mellin space, the box integral, here's the formula. How many people have seen this formula? Nobody? Some. Many of you seen. Perfect. Yes, that's right. Yes. Yes. Okay, so very good. So, in that paper, we did it for many other examples. We have a process, how you go to embedding space, how you do introduce Schwinger parameters, you do semantic trick. And so basically, we worked out lots of examples, and we find relations between different integrals, the differential equations that I've described. Okay, so we have the Mellin for the box. So we are working towards understanding the main result. So we go to we're taking this and go to Mellin space. So let me now go to the left-hand side. So the left-hand side, let me write down the corresponding energy correlated integral. So now so this was 1. This is now 2. So I consider myself done on point 1 for the box. Now I'm going to write for you the energy correlated integral for 3 points. So I'm going to write it, some of you have seen. So E3C, oops, it's going to be an energy correlated integral in n equals to 4 super Young-Mills theory in a collinear limit. So there are a lot of things have been studied here and there. I'm going to just take one formula. Okay? It's in so EEC, it's going to be a function of the variables. I will write, let me just write it and then I say it. So remember, it would be important, U and V's here. Who is a function of who? Who is a function? Yeah. So it's going to be an integral of what we call a 1-to-3 splitting function over the fraction of energy carried by particle absorbed by the detector. Let me write it. So this would be an integral, and this is the integral this is a projective integral. So this by this, how it's written. I'm just rewriting it explicitly. This is how it's written in the literature. Delta of 1 minus x1 minus x2 minus x3. So the way to think about it is you place some detectors at points Z1, Z2, Z3, and measure energy coming out of them. So now I denoted Zij is Zi minus Zj. So this is 1 minus 2, 2 minus 3, 3 minus 1. And then you integrate over some energy fractions called x1, x2, x3, and you integrate what we call in physics a splitting function. So I'm going to write one example, 2, 3. So please let me know if this should be crystal clear to anyone outside, especially who has not seen this. Plus the same term 1 switched with 2, where let's trace that I defined everything. So who are this? I call x1 2, x1 plus x2, x1 2 3 is x1 plus x2 plus x3. Yeah, who? Delta, yeah. Yeah, so what am I writing here? Yeah, this is in this sense, yeah. Good point, actually. Okay, I'll come back. Maybe when I write it, like, yeah. Sometimes, yeah, I want to go from project, yes. Yeah. Let me be vague on this. I think I'll be vague on this. So x1 2, x1 2 3. Let's 1 2 x s1 2 3. Yeah. Let me just make sure I define everything else. Yeah, maybe 2 z. Okay, let's follow along and see if I got this right. Z2 3 plus a x3 x1 z3 1. Okay, this appears. So we're going to take this particular. There's been a lot of work, and I'll talk about it for other. I'll have some slides showing these expressions. Any questions? Particular energy correlated integral. Okay. Yes, this is in the plane limit. The expressions. Yeah, there's an expert in the audience, Ching Ling, in the back, who's written these up to 11 points. I will have that on the slide momentarily. Let's just take this. Okay? This is like a leading order. This is the leading order. So we take this particular integral and we're going to relate it to the box. That's our assignment. And then we're going to try to ask a lot of, this is the beginning of the program. Then we're going to ask a lot of questions. Does this generalize to QCD? Does this generalize we can discuss this. For the Blackboard talk, I just feel this is what we do. Okay? The first one is, so there's a second term which switches 1 and 2. Where instead of 1, you put a 2. So you want me to write it. So S23. No, it's not systematic. It's instead of 1, you put a 2. So the second term is x23. Yeah. Okay. There's also a constant term, which I will not. Okay. We do this. So now the result. Okay. So now we're ready to do. I'm ready to explain to you the result. So again, So this depends. This energy correlate depends on 3 z's: z1, z2, z3, arbitrary. This is how you compute it, and I will have that. You compute it from taking a splitting function, taking the collinear limit, squaring it. So yeah, and go back. Yeah. So, but I'm just taking the final answer. From all what you're describing, I'm taking the final answer. Okay? And this is the final answer for after some work. So this integral has been computed and understood. I will have that on the slide, and it's been computed in 2019 by Moult and collaborators. I will again, and generalizations. Just wait. I'll get to my slides, but I just feel like I want to do this on the board. Okay. So 3. So how do we? So we take a result from energy correlator literature. We compare it to the box. I go to Mellinology space. This was the summer project for DIVU. Okay? My students didn't want to do it. I tried to ask my students at Brown. They said, no, I'm not doing this. This is old work, 2012. We want to do modern work. We don't want to do this. But anyway, he did it. And it's a 4-step process. So first, I was vague on the measure. You think? Yeah. Okay. I will show you the result of this. I will show you Can I just show you what we've done? Yeah. Maybe there's a better way to do it.
I think we can just
yeah. Yeah. Yes. Yeah. But maybe there is simpler way to get. Okay. The massive box and this integral. We want to connect this by going to our 2012 paper, by taking this and going to Mellinology space for the project by DIVU. So first, there was some subtlety converting this projective measure to non-projective measure. So actually, I was writing this, but now I will write this correctly. So step 1, we would write it as integral over, dx1, dx2. So now these are not related. They don't sum to 1. E to the minus x1, 2, 3. There's some. So it's okay. I mean, I should have started maybe with this. 1, 2, 3, x, 1, 2. So I'm going to only look plus, I'm going to only write the first term. Okay. Now we're gonna, it's really, again, a very simple exercise. So then what do we do with this? We first do Schwinger on this. We exponentiate denominators. So I'm going to write this as an integral. We're going to write it as d. So I just want to, I do want to do the counting. Introduce a Schwinger parameter for each of the denominator. And this becomes is still all this stuff. And the denominator, well, you'll know how to do integrals, minus C0, S1, 2, 3, minus C1, X1, 2. Okay? Everything in exponent. Now we're ready for Mellin. So we have e to the, I'll write for your formula. So now we're ready to do this, gamma. So I'm doing very schematic, but of course this is some work. Now for each, so this was a function of three z's, z12, z23, z31. For each we insert a gamma. Yeah, you all can do. I apologize, I'm very basic compared to what most of you did in this conference, but I think this is important. Okay, we do this, and we write, so we do Mellin on this, and so we would get, and I will write only the final formula, we get d gamma 1, 2, d gamma 2, 3, d gamma 2, 2, 3, 3, 1, of gamma functions, gamma 1, 2, gamma 2, 3, gamma 3, 1. I'm just, again, we need to get to that. So we are getting there. And then these, so remember S's had some X's. So these would be like expressions x1 to minus gamma 1, 2, minus gamma 1, 3, x2 continue, x3 continue, times z1, 2, minus gamma 1, 2, and the same with the other z's. Okay, now we need to integrate these 5. Yeah. So we need to integrate this 5, and I don't want to write these elementary methods. Very basic. You can do it all. So yeah. So we want to, after we do this, the final integral. So now first observation. So we're going to be trying to match. So we'll get rid of his x's. We're integrating them. We have some c's we need to integrate. But you can see already. Okay. So there's 3 gammas. We're going to be matching this with this. There are 2 deltas. Yeah. So one of the integrals will give me a delta function on sum of gammas. Let me write for you the final result. So we integrate these 5. So these 5 we integrate, and we get, at the end of the day, the following answer, which we will then compare. Gamma 2, 3. And then we have a prefactor. I will... minus gamma 1, 2. And then we have gamma squared. So I will say y squared appears. Getting there. Again, it could be very well be that there's a simpler derivation. Maybe you can all, but my goal here is so that people start thinking about this. This is my goal of my talk. Because I couldn't convince my own students to think about this. So, very good. Times z12 over z13 minus gamma 1, 2 plus 1 z23 over z13 minus gamma 2, 3. Okay, there. Main result by collaboration by D. Okay? We now compare. So what I've done, I've written for you the Mellin space representation for the integral on top, which is this. Now we can start comparing. Yeah, you can see. This is the box. Gamma squared, gamma squared, gamma squared. Gamma squared, gamma squared, gamma squared. Yeah. Variables, except for this. Okay. And this is, so we have the box. And this is what these objects are. Tilde in the box. Okay, what should I erase? I will. No, tilde means I will describe what tilde is. Tilde means this denominator. factor. Tilde means the denominator factor, and d means this numerator factor. Okay, this is our main result for this particular simple integral. Any question? It could be you have a simpler. Many things you can do in both. I want only for this purpose of the talk to compare to this. Yeah, many things you can do on both sides. Yeah, just I want to compare this to this, and indeed what we observe, right hand side equal to left hand side up to the box, up to this factor. Okay, so now let me. So I have only one last thing to say. No, that's exactly what we need to discuss. And that's exactly where the hard work is going to be for higher points. And this is exactly what I want to say. Okay, so, yeah, I can't do this exercise. Yeah, no, don't. Yeah, I just need this, yeah. This is fine. Because I'm good. You think this would be better? How much time do I have because I have slides? 20 minutes. 20 minutes. Perfect. This is actually not so perfect, but I will. At least Okay. Very good. So, formula on the left-hand side, formula on the right-hand side. Obviously, du is gamma 1, 2, and dv is gamma 2, 3. And then u equals z1, 2 over z1, 3. b equals, okay, z2, 3 over z1, 3. So numerators are easy because you just act, numerators are easy, you just act with d hat, which is, u d by du. This is the schematic, and you pull in the factors. And you have the, numerator, no problem. Denominator is a problem. Denominator is very similar to what we saw in our work with Miguel and Mark in 2012. And that is what we call deformed box. And I did write the formula, which is actually quite a little bit visible. So for denominator, we would have to take the box and do it different. So we still would have one integral to do. And this would be box of u and v. So there is some reshuffle, and you can see that. So you have to do this deformation, and then you can convince yourself that ln of this is the formula we've written. So this is where the hard work lies. We were hoping that this would be just numerators. Yeah. Okay, so now, again, why is it interesting? Well, I'd like to switch to my slides now, but I can talk. So we've reduced the energy correlated integral in n equals 4 in collinear limit for this particular example I explained to you to a integral differential operator acting on the deformed box. So are we? So now there's work to do. It could be there's simpler derivation, and I would love to hear if you have a simpler derivation. I would love to hear this. So there are two things we can observe. Like this? Okay. Yes. Now, okay. By the way, this now I have my slides. I'm going to do n equals high n. So this is where we are. This is where we are. So how many, 15, do I have 15 minutes? Yes. So this is what we've done. We have derivatives of deformed box. Now, let me also show you the result, of course, for the energy correlator. This is actually the actual result. That's, so this is, so if you do that left-hand side, you get something like this. And the thing that, so why is this of interesting to me? Because we understand box and gons and stars, we call them stars, and we understand the left-hand side very well, right-hand side, sorry, we don't understand energy correlated because we understand right-hand side very well. And we can talk about things like symbol alphabet. For example, the arguments of the polylogs that were described in the previous page are given by A2 cluster algebras. And I'm still think there's actually a better formula than this formula, but we'll get there. But anyway, we can now use all the machinery that we've developed in Amplitudes program for energy correlators because we've related one to another. So let me just say, one thing is symbol alphabet, but the other thing I should mention, I finish, is that we would need to understand this. And technology we've been developing with Kai in particular, she's been, so you know the symbol of the box, you want to compute symbol of the box, tilde box. So Kai has, you can write some differential equations for this, but she's done an amazing way to do it, but technology is still, not there. It would be nice that eventually there's, knowing symbol on here, how do you get the symbol of the box? Yes, can you, yeah. Yeah, this is not the one loop box alphabet. That's correct. Yeah, this is the alphabet. Yeah, this is what, these are the polylogs that appear here. That's all I've written. These are the arguments, yeah. But we have not written this in a manifest A28. So all I can say, and actually I don't think that's in the paper. So they write in the paper, in the review, that this is the alphabet, but this is A2. Those of us who know cluster algebras know that this is A2. Okay, but no, okay, higher points. So left-hand side, right-hand side, okay? By going to my left space. So this is picture the best I can do this weekend. I stayed Sunday whole day writing this. So please, whole Sunday I spent writing this slide. So left-hand side, what is known for higher points, okay? Good, so important. So I am skipping a lot of references. I'm just telling you what we need to develop right-hand side, left-hand side for this. So the collinear limit for n equals to 4, for 4 points, we go to 4 points, have been computed in this paper, Chicherin, Mould, Sokachev, Kai, and Zhu, okay? They are, so you can write down the answer for 4 points energy correlator. There's a different integral, there's an integral which and you can do it, and now you can recognize some of the ingredients. It's an integral, it's a function of Zij, and it's given by sum of some prefactors times some polylogs. And now if you go to the auxiliary file in their paper, you can get, you can, please go. But it's 51 term expression, heroic work, amazing work. So this is the only 4 point that there is. For the integrated, this is for the answer of the energy correlator, answer. So fascinating thing that fascinated many of us, I learned this I think from Andrzej first, but I've been talking to any mathematician I see who does cluster algebra, is that if you look at this, the alpha, so they have this expression, but if you look at the alphabet, so they have some polylogs, and if you look at the polylogs and the alphabet of those polylogs, they involve cubic roots. So for us, those who've been working forever on cluster algebras n equals 4, we've seen square roots. Is Omer? So square roots you can get from a quiver with 2 dots and 2 lines. And this is the best way. You can infinitely mutate. Those who knows cluster algebra, Christian, and you get square roots. How to get cubic roots? So we've posed this question. It's a very simple question to mathematicians. Find a quiver which you mutate infinitely that gives you cubic roots. I still don't know the answer to this. This is very, very interesting. But
I have changed some.
He does it, yeah, but he's not a mathematician. Okay. So this is a question to Lauren Williams and people around Lauren. So very good. So that's the answer for 4 points. What else do we know? The integrand. So the integrands that I written for n equals to 3, and that was used by Kai et al. For n equals to 4, has been written in this remarkable paper by Chinlin, who's here, and Yao Shi, who is a postdoc with Livy and Tomic, in this paper. So this is some of you heard this, but I think it's quite fascinating. So they wrote down the actual integrand. So the analog of what I wrote for 3 points up to n equals to 11. And this is just a slide on how they do this. in a particular collinear limit. This boils down to computing some splitting function and squaring it. But anyway, so this is, for example, an integrand for for 4 points. So analog of what I've written there. I mean, if you heard some songs talks, you've seen this. So analog of what I've written in that part of the board, this is analog for n equals to 4. So this is 3-point integral is 4 because I didn't write two constants. And this would have 21 terms. Qingling is an expert. If you go to 5, 6, 7, 8, so it's minus 3. So this is how many terms. And they have them in the paper up to n equals up to 7 points. And if you want to request higher than 7, you can ask Qingling. So the integrand is known. Okay? So work can be done, extending our result. New features, they pointed this in the paper. Of course, new features of these integrals, you can start looking at them. For 5 points, they point out first elliptics appear involving fourth roots. In n equals 6, hyperelliptic integrals appear. So from these terms, I really think it's time. We've developed a lot of technology for ordinary integrals. It's a good idea to look at these. Okay? Yeah, then this was collinear. Oh, oops, why did it not go back? Oh, yeah. So this was all collinear. So because you can ask, what about arbitrary angle? So arbitrary angle, since we have Yangzhan and Roruma, they have the paper. And also, I like to cite everybody who's in audience to make a connection. And Andrzej also developed the bootstrap approach for some of these for arbitrary angle. So that's all we know for our purposes. And I'm not even touching QCD. So this is what we know on the energy correlator side. So integral up to 4 points, I repeat, has been evaluated in this paper by Chicherin et al. 51 terms. You can open them. But integrand, Qingling, up to 11. Good. Right-hand side. Right-hand side we know. So right-hand side are Feynman integrals. And one loop n gone in n dimension. That's the right-hand side of the box. For that, I refer you to my talk and the paper, which is done with Christian and Li Cheng. This paper was ahead of its time. It has only 6 citations, but I think I viewed it probably one of the better papers, very good paper. But anyway, we've written any one loop n gone in n dimensions as a volume of orthoschemes. This is the forefront of mathematics developed by Rudenko. If you heard, some of you heard my talk on CERN in 2023, this is just a copy of my slides. So, and yeah, so lots of mathematics. I'm going to just skip those slides. Yeah, I just show you, some of you maybe remember them, some of you not. It's a beautiful work, beautiful mathematics. Nobody really used it yet, except when I was preparing this talk, I just wanted to see how this work is doing. It has 6 citations, and actually Claude Dour had a student who processed our paper up to n equals to 5. I say this and applied to some integrals. Anyway, so forefront of mathematics, Rudenko's formula for the volume of hyperbolic artschemes in principle gives us, and when I say in principle, I want to show you this. For example, all massive hexagon in 6 dimensions with all massive. You can do numerical, write the formula for Rudenko, do numerical check. Credit goes to Christian and Li Cheng. So transcribing the paper and doing all the work. So yes, I reference them. I reference this. 6, yeah. I don't want to. I can show you. This is for one loop, all n, any n gone in n dimensions, any mass. This is, yeah. I reference you. You referring to this? Yeah. No. I think you told me to reference this in my CERN talk. So yeah. I know. Yeah, but n gone in n dimensions, one loop, any massive. So that's. Do you have n gone in n dimensions? how does that compare to Rudenko? You need to use this Rudenko formula. Hyperbolic, yeah, with all masses. So it was an extension. What we've done was extension of this paper. How does your work compare to that? We can look. We can compare. Christian is next to you. We can compare. We did. Yeah, but anyway, I do feel our paper is a little underappreciated, but it's ahead of its time. But hopefully we can, this is cool stuff. Now, yeah, I view it one of the more important papers that I co-authored. Okay, so left-hand side, so we have energy correlators up to, I told you, and then we have in principle right-hand side. Okay, what did we do actually? So what did we did, so let me show you our result for 4 points. It was easy to do this on the blackboard for 3. It gets much more complicated. We need powerful young people. If anyone is interested, please. So we were able to reduce, remember I told you there are 21 integral terms in the integral expression that then were reevaluated. So everything reduces to these 5 integrals, and these are some deformed integrals. Yeah, so that's the 4 points. But the dream is to do it for any. The complexity are those. So why it's complicated? Because of these factors. So it becomes, technically, yeah, we had an undergraduate student look at this, but I think as the most senior person starts looking at this, a young person, I think there would be even better story. So for example, like you just show you explicitly take one of the 21 terms, and that reduces to this four massive hexagon in this some particular kinematic. So, but again, this is deformed. So you will have to develop some then technology to get the symbol to derive the result. So very good. So now I conclude. So I've been telling you that we've been exploring Mellin space representation for collinear limit of energy correlators in n equals to 4. We reduce the computations of 3 and 4 point correlators to the derivatives of deformed box and hexagon. Now, the right-hand side, the n-gon and n-dimensions have rich structures such as cluster algebra and a lot of properties, geometry, etc. So energy correlators inherit this. This is why this is interesting. I want to end this talk with my favorite slide from Bird, who reminds us that success, okay, I've been doing this, I've been working on amplitudes much less than him since only 2003. But in the past 25 years, it grew. And success of this program relies on 2 pillars. Anytime somebody tells me some exciting results, I do a litmus test. Do you have 2 pillars or not? So there are 2 pillars. On one hand, you have the mathematics. You have the structure, symmetry, beauty. You have mathematical structures that you see, but that's not enough. What you want to do, you want to use this structure in order to compute something, and preferably something that has not been computed, and preferably something outside the field. So to thrive, one really needs support of both pillars. And with that in mind, let me just say what are the 4 fronts for this particular correlators. What is the 4 fronts on both sides? So on the left-hand side, I already mentioned this, but I think it's good to summarize in one slide. So we're far from this. So for mathematics, I think it's important. I showed you some examples. I showed you that for 3 points, these are alphabets of A2. It's very important to develop this cluster algebra approach more and understand the structure of the energy correlator side. And for mathematicians in particular, it would be nice to have an understanding of this cubic root. So that's a very precise, if anybody wants. So we had some fun in SwissMath talking to some mathematicians, but nobody told me how to get the cube roots. The problem is very easy to formulate. Now the right-hand side, more. We want to compute. So far you can say, hey, what did you do? I just, 3 points and 4 points have been computed for energy correlators. But so the 4 front is next to compute the 5-point energy correlator. And then if you ask about QCD, I think the 4 front is to get the splitting functions from Doer and others from 20 so these expressions were based on some nice way of writing these splitting functions. So for QCD, they're the expressions, they're in Mathematica. My understanding is that's the thing one would do. Yeah, and with that I stop. Thank you.